In the second part of today's lecture, we're going to look at VSEPR geometries that are derived from molecules in which we have 4 regions of electron density around a central atom. So here's our central atom. We have 1, 2, 3, 4 regions of electron density about it, and they may be bonding, they may be lone pair of electrons. And what we showed in an earlier lecture, the best way to distribute regions of electron density about a central atom when there's 4 regions is in a tetrahedral type of geometry. Now, when there's no lone pair of electrons on the central atom, we discussed the AB4 model. The AB4 is a central atom A that's surrounded by 4 bonded atoms B, and they adopt a tetrahedral molecular geometry, which is identical to the electron domain geometry because all regions are involved in bonding. And we said that the bond angles in these situations are 109.5 degrees. And I actually put together a big model for you. That's sort of like what a tetrahedral looks like. Pretty good description. These bond angles are 109.5 regardless of how we rotate it. An example of a molecule that we discussed that follows this type of geometry is CH4, which is called methane. We have a central carbon surrounded by 4 hydrogen, and the bond angles between all of them are 109.5. What we're going to show in this part of our video is that we can derive 2 other geometries from this generalized structure. And these are going to involve the AB3 E1, which has 1 lone pair, and an AB2 E2, which has 2 lone pair. So let's begin with 1 lone pair. And again, it's derived from the tetrahedral electron domain geometry because there are 4 regions of electron density about our central atom. However, one of them is a lone pair of electrons. And for simplistic reasons, let's put the lone pair on top. And now this molecular geometry has a name to it that's similar to one we called earlier, but it's slightly different. This is trigonal pyramidal. Notice it's different than the trigonal planar. This is trigonal pyramidal. It's like a pyramid that sits in the desert in Egypt. Remember, we don't see the electrons, all we see are the atoms below it. Let's pull up our model here, and let's remove one of those. And let's put our lone pair of electrons on top. There would be our lone pair of electrons. And what we find is that this atom is sitting slightly above the plane, and these all sit in a plane that make a triangle, just like a pyramid. Now notice it's not trigonal planar. Trigonal planar, they would all sit in the same plane. This one, the central atom sitting slightly above it, and the bond angles are going to be somewhat compressed from the original 109.5. Once again, what happens is the lone pair of electrons sort of spread out, and what we find is that the bond angle is going to be less than 109.5. We're going to find that in most cases, it's going to be about 107. Let's look at a molecule that follows this type of geometry. Ammonia, NH3. Now, we drew the Lewis structure for this molecule at the very beginning of our lecture dealing with Lewis structures. We have a central nitrogen atom. We have 3 hydrogens around it. And we have a lone pair of electrons. Let's put them in a shape that shows it's sort of like it's in an orbital. Okay, first thing we need to recognize is what's the electron domain geometry. Now that helps us to understand the true molecular geometry, because it gives us a general framework of how electrons are situated around our central atom. So let's count the regions around it. We have 1, 2, 3, 4. 4 regions of electron density around our central atom. So this implies to us that the molecule is going to be derived from a tetrahedral type structure. But what we want to do is we want to define the actual molecular geometry. Well, we would follow this model right here. We would have a central nitrogen. We have a lone pair of electrons. And we have 3 hydrogens that sit in a base around the bottom of that nitrogen atom. And this would be trigonal pyramidal. Bond angles are about 107 degrees. Notice they're compressed from the original 109.5 that we would expect a tetrahedron to adopt. So NH3 follows this type of structure. Let's look at the next situation, the situation in which we have a central atom with 2 bonded atoms and 2 lone pair of electrons. Now this is what we call an AB2E2. And just simply from the regions based upon the subscripts on the bonded and lone pair of electrons, we could see that this is derived from an AB4. Notice these add up to 4, 2 bonds, 2 lone pair. There's 4 regions around the central atom. And let's put our lone pair to be consistent with this model over here. And what we find in this particular model is we're going to get a geometry that has a name similar to something else we looked at a few minutes ago. This is called bent, just like we saw earlier, but we're going to discuss how it's different in a few minutes. In these cases, the bond angle's been compressed quite a bit. The bond angle is down to 105. So let's imagine what we've done now. Okay, that was the AB3E1. So what we're doing is we're putting another lone pair of electrons on this model. And there's our lone pair of electrons. So we have 2 lone pair of electrons, and we have the atoms that we see in the bond. And this is a bent molecule, bent molecular geometry that hopefully we can see there. 2 lone pair of electrons. It's derived from a tetrahedral. And the bond angle, which is important, is 105. And that's what the model is going to look at. Remember, what we see are the atoms, not the lone pairs of electrons. They're tiny. Let's think of a molecule that follows this type of geometry. Water, H2O. If we go through the steps for writing the Lewis structure for H2O, what we find is that we have a central oxygen atom bonded to 2 hydrogen atoms, and there's 2 lone pair of electrons on our oxygen. Now, normally that's how we write it. And a lot of people make mistakes and they're like, oh, that looks linear, but it's not linear. This is not linear. This follows this model here where we have a central oxygen and we have 2 hydrogens and we have 2 lone pair of electrons. Sometimes we draw these with what we call bunny ears. And the bond angles are about 105. And this is, again, a bent geometry. So this is where the question arises, where people are sometimes need to explain. SO2 and H2O are both bent. Why are they different? How are they different? And why are they different? So let's look at the differences between them and explain a little bit about their differences. SO2, as we said, is also bent. Now, let's look at how they're different and why. First of all, one thing we should recognize is that there's differences in the bond angles. SO2 is 116, water, H2O, 105. Second thing is notice a single lone pair of electrons. Water, two lone pair of electrons. These are some real big differences between them. And this is manifested by the electron domain geometry, the regions of electron density that define how these structures are formed. This has an electron domain geometry of trigonal planar. Water, this has an electron domain geometry tetrahedral. So these are some really good ways to describe these differences and why they're different. Bond angles differ. There are different numbers of lone pair of electrons, and they're derived from different electron domain geometries. So that ends the discussion on molecules that are formed from four regions of electron density about a central atom. In our next lecture, we're going to move to central atoms that have lone pair of electrons and can also experience expanded octets. Thank you.